Hello everyone. Welcome to our webinar for this month, Australia's coastal ecosystems and how we're monitoring them. We're very excited to have you all join us. Thank you for doing that. And from all over Australia and many countries of the world, it's great to see you. So to start today, and in keeping with the spirit of reconciliation, we at TERN acknowledge the traditional custodians throughout Australia, New Zealand and all nations. We honour their profound connections to land, water, biodiversity and culture, and pay our respects to the elders past, present and emerging, and acknowledge the important role that Aboriginal and Torres Strait Island people continue to play within our community. Today I'm joining you from Jabukai country in far north Queensland, among the rainforest people. Feel free to put where you're joining us from in the chat. So again, thank you for joining us today. And for those that haven't met me, my name is Beryl Morris and I'm the Director of TERN, Australia's Ecosystem Observatory. So feel free to put any questions you have in the Q&A throughout our webcast. That's at the bottom of your screen, I believe, and we'll answer them towards the end of the webinar. But if you have any technical issues, pop those into the chat and we'll try to fix them up as the webinar goes. You can also use the chat to contact other attendees today. So I wanted to acknowledge also all of the groups that make it possible for TERN to run national research infrastructure. We're funded by the Australian government and we have co-funding from a number of our state governments. But really it's a federation or a partnership of universities and CSIRO across the country and internationally, and it's a growing collaboration and we're very proud to have that one. So thank you for that. So today we are going to be joined by three speakers, one by one, who are going to talk about aspects of monitoring the coast. And as we know, coasts across the world are facing lots of problems, and so we want to look at the special challenges that come from trying to monitor them. And our speakers today, in the order that they're going to speak, are Associate Professor Ruth Reef from Monash University, who's the head of the Coastal Research Group in the School of Earth, Atmosphere and Environment, and a leading authority on Australia's coastal ecosystems. She's going to be followed by Madeline Goddard, or Maddie, who is joining us from, she's enrolled in a PhD at Charles Darwin University, and she's a coastal scientist dedicated to understanding the impacts of climate change on coastal wetlands. And she has had many roles already, even though she's still doing a PhD. And she'll tell you more about her work in Darwin Harbour for the Northern Territory Government and internationally. And our final speaker is my colleague, Dr. Tim Ruling, who is the CEO of AUSCO, which is Australia's provider of research infrastructure to the geoscience community, working on fundamental geoscience questions and grand challenges. And Tim is going to tell us how that all fits in with coastal research infrastructure. So I'm now going to hand over to Ruth, who is going to start us off today, and I'm going to turn off my camera and I'll see you again during the Q&A. So thank you.
Thank you for the introduction and welcome from Melbourne, where I'm on the unceded lands of the Kulin Nations, and I pay my respect to the elders past, present and emerging. I'm going to share my screen. And yeah, and I'm going to talk to you about how we've been measuring greenhouse gas exchange between the coastal land surface and the atmosphere in complicated systems such as coasts. As you can see from this image, coastlines can be inundated, can be dry, depending on tidal cycles, depending on seasons, and there are kind of multiple non-linear forcings that are occurring all the time on coastlines. And I think by the conclusion of this short talk, you'll recognize the importance of these long-term monitoring programs, such as those TERN is providing platforms for. So measuring greenhouse gases are CO2, methane. We'll be focusing on the carbon-based ones, so mainly CO2 and methane. But this is part of a larger project where we're actually interested in water. So we're looking at the hydrology of water, how the ocean and groundwater interact on the coastal zone. But while we measure that, we get CO2 information, and I'm sure this is of great interest to many in the audience. So where are we working? We work currently at 2 sites, and a third is coming. We've had a eddy covariance tower, and I'll come back to what that is, at French Island for a number of years. French Island is one of the islands in Western Port being the bay just east of the city of Melbourne. So it's part of a graben system that is a sunkland. The sunkland has a few elements sticking out. You can tell I'm an earth scientist. And one of those is French Island, which has a very large undisturbed salt marsh, temperate coastal salt marsh community. It's a Ramsar wetland. It's highly protective. French Island is not much inhabited, so it's a very relatively pristine system, very interesting. But it also represents a coastal ecosystem we don't talk about much, which is the temperate coastal salt marsh. It's quite different to the salt marsh you would see elsewhere. What we have maybe representing more of Australia is our site in Moreton Bay, Southern Moreton Bay in Queensland, where we are working actually together with colleagues from Southern Cross University, mainly with Professor Brad Eyre, where they are measuring a few parameters, and we have, I don't know if you can see it here, we have an eddy covariance tower within mangroves. The mangroves there are Avicennia marina dominated, although there's some Rhizophora and some Cereops and a bit of Agiceras, a few Brugera, and that is the extent of my botanical understanding of the diversity here. But there's also salt marsh and melaleuca within what we'll call the footprint. The map represents climate zones in Australia, and we have a very different climate zone represented, CFB being more temperate, CFA, again, coastal. These are the Köppen climate classification, but kind of a more subtropical system. We're about to erect another eddy covariance tower, and that will be going into the kind of arid landscape of the Exmouth Gulf. We're still in discussion with traditional owners in that area in terms of access and how to best incorporate traditional owners into this deployment. So what does an eddy covariance tower look like, and what is it measuring? So here's an example from Moreton Bay. Of course, you see a solar panel. This system is quite power hungry, always a challenge in wet environments. The solar panel kind of leads to some battery bank, and that provides stable power to the tower. It's very important that the power is stable. The tower is needs to be above the vegetation. We'll come back to that. So how you need to go depends on the height of the vegetation, and it can be quite restricting in these environments. Here you see a ladder of maybe 3 meters height. So this is a pretty tall system, and they're pretty tall mangroves, but not as tall as, for example, in the Daintree. So things to consider when you put out a tower is how tall is the forest. On the tower, we're measuring a few things. You can see this pronged instrument is an anemometer. So this measures 3D movement of air at very high frequencies. It's using so you might know the cup anemometers, but this one is using sonic. It's a if you are more familiar with currents, it kind of works like an ADCP of airflow. You see this big instrument over here measures methane concentrations. We have an instrument here that measures CO2 and water concentrations. The Ergoson actually includes its own anemometer within the measurement volume. Then there are a few, the modem that sends data to us here in Melbourne. We have boxes where data processing occurs. All the data is collected at 10 hertz. So you can imagine there's a lot of data, but it will get collapsed to half-hourly averages of flux, which I'll explain in a moment. The tripod next door has things that enable us to measure the net radiation balance. So how much incoming shortwave, outgoing shortwave, long wave radiation is coming through this system. In addition, there's temperature, humidity, all the things we need to know what the flux of water, CO2, and methane is between this land surface or water surface and the atmosphere is. I'm sure you already understand there are other lateral fluxes happening of material. The ocean comes in and out. There's interaction between the water at the surface and the water in the ground. We are only looking at the fluxes between the surface and the atmosphere. And how does that work? So here's a French island where we have very short vegetation, 40 centimeters or so. This is a salt marsh on French island. You can see much less inviting, very cold and windy, and we'll come back to how that's a problem in these systems. Very cloudy, right? Low light levels. You already see a double solar panel here. And much shorter tower. We don't need to get very high above this canopy. And this slide has a lot, I'm sorry. But we have wind, say, blowing from left to right across this image. And if the wind is blowing high above the surface, say 10 meters above the salt marsh, we kind of, the wind is kind of blowing uninterrupted from left to right. Lower than that, we start to feel boundary conditions. So there's kind of a bit of a turbulence that happens through friction. So the wind blows through, kind of engages with the topography and starts to form flows that look like eddies, right? That are create these eddies. And eddies can come up this way or that way. And what's important in the eddy is that it has a vertical component of speed, right? So we have either speed going up or speed going down. So we have a movement of air that's vertical, and it represents to us periods of time where we have air that, say, came from the ground and heading to the atmosphere, or from the atmosphere to the ground. And if we measure these eddies coming through frequently enough, and we measure the concentration of gas within them, and we do some fancy mathematics, we can work out fluxes. And another thing that's occurring this entire time is there's a radiation imbalance. So the sun, say, is shining and the ground is warming up, and we're generating air that's a bit more buoyant close to the surface, so it rises up. And these two processes together, the buoyancy of air and the friction that's causing eddies, is creating these vertical flows. So these vertical flows are allowing me to estimate the flux from and to the atmosphere. There are a few assumptions we need to make when we are working with these simple physics principles. And one of them is that these eddies indeed occur, and also that my buoyant air can rise and that I have some buoyancy. And these are not satisfied when, say, the atmosphere is in very stable conditions. And we're going to see in a moment what happens, say, at nighttime, where I don't have that radiation imbalance, or during periods of low wind, or periods of actually very high wind, where I have a poorer eddy formation. Another thing we assume is that the surface is homogeneous and flat. And we cannot assume this in tidal areas, which adds a layer of computation. So if I look at French Island and I think about these eddies and how air is rising and coming down, I'm wondering where the air is coming from. And I can trace back these eddies through computation back to their origin. And you can see here, I've kind of marked the origin. And when we add those origins up, we call that the footprint of the tower. And you can see that the footprint is usually quite concentric around the tower, depending on where the wind blows from. And if the tower is, say, here in the middle of the innermost circle, I can see that I'm capturing more and more fluxes as I get away from the tower until the point where, the mathematics don't add up anymore and whatever is rising isn't coming to my tower. You can see that during different periods of the year. So here are two wind roses. Sorry, I think I made the wind like current, but here are winds. When I have winds blowing north, blowing from the north, I have my flux footprint is kind of more northward than during the winter time. During the winter time, where I have a lot of southerly wind in French Island. So footprint models change with seasons, and it's always important to note where you are collecting from, especially if you have a heterogeneous salt marsh. In our case, wherever the wind came from, it was just salt marsh. There's a very thin layer of, those little Victorian mangroves over here, but you can tell that actually during many years of tower operation, we've never actually captured the mangrove, where the tower is not high enough for that. During these periods, there's huge seasonality, which is quite characteristic of this climate zone. And you can see here the daily maximum temperature and daily minimum temperature, and you can see big variations between winter and summer, although you can also see that, it's never too warm in Melbourne. I've shaded a few different periods that we'll talk about later, and I've called them the growing season and the dormant season, and we'll see why in a moment. So we have periods where the atmosphere is perhaps too stable to generate flux, and things like that create small gaps in our data, more frequently at night than during the day. But there are also some bigger gaps. And bigger gaps are to do with a lot of these instruments need quite a lot of babysitting, a lot of connecting wires, working out what's wrong. The USB is overheating or too cold. Problems with flooding of instrumentation, problems with, we had a big storm that took away the solar panels. Sometimes you have large gaps. And when you do projects like these, you should expect some large gaps in your data. Now, for small gaps, we have ways to fill in little gaps computationally. Whatever I'm presenting to you now has not been gap filled. So Moreton Bay, we have far more stability. We don't suffer from storms as much, and we don't have really long periods without sun. On French Island, a lot of the gaps come from lack of power because there are many days that are very short, where cloud cover is so high that solar panels are quite ineffective. And over time, we lose battery power, even though there are 4 batteries. So there were more gaps. Moreton Bay, we've put in the tower in August, and it's been running till now. So here we are, end of March, or end of April, sorry, and it's been collecting data all this time. So what we can see here is a thing called a fingerprint plot. You can see the time of day, 0 till 24. Okay, so noon is 12. And you can see the day of the year. You actually can't see it because it's broken up from 1 to 365. And so I can see August about here, December here, March here. but these are 0 to 365. And each one of these points is a half-hourly flux measurement of CO2. And flux we measure as it's called net ecosystem exchange. We measure it, in this case, in micromole CO2 per meter square per second. So these are things that can be scaled up in space and time. And on average, if someone wants to know, this system is taking up CO2 as a sink for CO2, atmospheric CO2, with about negative 0.46 micromole CO2 per meter square per second. Of course, there are much fancier ways to analyze this data set that we utilize. We can look at temporal changes. So this is a long-term average of hourly gas flux, and we can see positive means gas is flowing to the atmosphere, or red in this case, and negative, which is blue in this case, means gas is flowing from the atmosphere into the landscape. We don't know where in the landscape exactly, but it's in the landscape, most likely photosynthetically driven. And we can see when such fluxes occur. So this is, again, 0 to 24 hours. Nighttime, we don't have photosynthesis. We just have the respiration of the landscape. We can measure respiration rates. Daytime, we have photosynthetic uptake. And like I said, if we look at the net, it's a net autotrophic system, takes up CO2. But there are huge variations through time, and you can already kind of sense it here, where you can see this is the kind of wetter season in Moreton Bay in Brisbane, or this is Gold Coast, and this is that drier season, and you can see it's bluer over here than it is over here. So we can sense that if you come any day of the year to measure this, you might get a different result than you would from a long-term record. This is very extreme on French Island. French Island has a salt marsh that is temperate and quite optically seasonal. One of two of my students are Indigenous students from the region, and they have a name in the Kulin Nation for the colors of the salt marsh through the season. It's actually interesting that seasonality in salt marsh is reflected in the Indigenous calendar. And but using PlanetScope, you can also see these are 4 periods in the year, and this is NDVI of this particular salt marsh. And we can see from PlanetScope there are big changes in the greenness of the marsh, and those of you familiar with those temperate marshes would be familiar with this, although surprisingly it's not in the Australian literature. So I look at things like CO2 flux, like we did before, hourly. This is evapotranspiration, so how much water is lost from the landscape. Like I said, we're very geared towards understanding the hydrology of these systems. And this is shortwave insolation, radiation, so light, basically, mostly visible light. And you can see big differences in both the length of the day and the amount of radiation between what we call the growing season, like the warmer months, and the cooler dormant season of the marsh. So whilst evaporation is quite similar, the CO2 flux is much smaller during the dormant season. It's still a net positive in the sense of a net sink of CO2, but only just. Whereas in the growing season, the CO2 sink is very clear. And other things affect, we can take these long data sets and start to look at what's affecting carbon uptake by these systems. We can see things like air temperature, which looks a bit messy, but if we just look at net, now I've converted it. So positive is, if it's a positive net ecosystem productivity, it means CO2 is being taken up. And we can see that CO2 is being taken up more during kind of optimum temperature ranges. We've done some analysis here. There's about a 23, 24 degree optimum. But there are also like very hot days can result in, which won't be a surprise to plant physiologists if they're here, will result in closure of this system. Also very cool days, by the way. So light, light response, of course, we can extract from this water use efficiency, how VPD is impacted, things like that. But of course, that's CO2, and it is methane. And CO2 showed some predictable patterns. We expect daily, diurnal range. We're seeing some seasonality with NDVI. I mean, like CO2 is predictable. Methane is absolutely not. So if I look at what methane is doing, methane could be doing nothing for a long time. And then there would be often linked to spring tide, but not always. Sometimes linked to rain, but not always. There will be large activity. And activity can be both an emission or an uptake. And here's just an example of, I think, a 2-month record, maybe a little bit more. And you'll see that even just during this period, there is a net emission to the atmosphere. And while the numbers doesn't look big, the equivalence is actually greater than the CO2 uptake for that period. So actually, this is a net emitter of greenhouse gases. And we wouldn't have picked that up if we just put in some chambers any day of the year. And I think this really highlights both the effect of seasonality, the effect of, kind of nonlinear events, that these greenhouse gas fluxes really should only be studied with these long-term monitoring data sets that can be enabled through programs like this. I'm going to end here and thank, obviously, the Kulin and Quandamuka nations on which land this has taken place, especially Ebony and Drew, who have been really great to have as students to hear about, like, kind of the Indigenous perspective of these marshes. I'd like to thank other people involved in the project. It takes a village to keep these things ticking along, and to thank the Ozflux Network for a lot of support, especially Dr. Caitlin Moore. And thank you very much for having me. At this point, I will stop sharing, and I believe I will hand over to Maddie. Thank you.
Great. Thanks, Ruth. That was really fantastic and a nice little segue into a coastal monitoring method I'm going to be talking about. I think some of our sites overlap. Well, not my sites, but I think there's some overlap there. All right. So I'd first of all like to acknowledge the traditional custodians on the land on which this research takes place, the Larrakia people, and pay my respects to elders. So thanks for joining us. Here I'm going to present on just one method for monitoring coastal wetlands. Coastal wetlands are mangroves and salt marsh. That's my definition for this talk. And I'm going to be talking about surface elevation tables, sets, otherwise known as rod surface elevation tables, RSETs, and I might use this term interchangeably throughout. So this is part of my PhD research, but I'll also be talking about the research of many other coastal wetland researchers, and I'd like to acknowledge the work of the emerging network of RSET practitioners around Australia, but also internationally. So coasts are a dynamic zone. They're in between the land and sea, and as such, they're often in flux. And the mangrove forests and salt marsh that occupy this space have some very interesting emergent properties. To delve straight into this world I'm going to be talking about, I'd like to invite you into the mangroves. It's just a 2-minute snippet from a film my partner and I made for National Science Week. Between the land and the sea lives a very special forest. Mangroves are home to many animals, including fish, birds, snakes, and crabs. These forests protect our coastlines from damaging storms, and they also capture lots of carbon from the atmosphere, and they store it in their mud. Blue carbon ecosystems refer to mangrove forests, seagrass meadows, and salt marshes. These ecosystems store large amounts of carbon as their soil is always wet. These are some of the free ecosystem services mangrove forests provide to us. Mangroves play a role in combating climate change. global sea level rise presents a significant challenge. Too much water and mangroves will drown, and they can't survive on dry land. However, there is hope. Given the right conditions, mangrove forests can move. I'm Madeline Goddard, and my research is looking at how mangrove forests in Darwin Harbour keep pace with sea level rise. As well as moving landward, mangroves can move upwards. Mud settling on the forest floor can gradually lift the entire forest. And their amazing root systems also do some of the lifting. In this way, mangroves have kept pace with slowly rising seas. We hope they can adapt to our current trajectory of rapidly rising sea levels. Okay. I'll stop it there. You can view the rest of the film on the Sightlines journal online if you're interested. All right, so the sea level is rising, and thermal expansion of water and the melting of polar ice has increased the volume of water in our oceans. But the ocean is not a bathtub with a uniform sea level rise. Changes in land height, ocean circulation, and density all cause regional variation. So it's this regional sea level rise plus the global sea level rise that will result in the relative sea level rise of a given geographic location. So why does this matter to our coastal wetlands? Well, mangroves occupy the space between just below mean sea level and the highest astronomic tide, and they're highly adapted to exist in this tidal zone. Existing mangroves and salt marsh need to adjust to sea level rise, or they'll be inundated beyond their physiological tolerances, and we risk losing them. But mangroves can adapt and have persisted despite changes in sea levels over millennia. The responses of mangroves may be, firstly, that they keep pace via sediment accretion and biogenic root contribution, so adding soil volume and moving up. And the hydro period is the amount of time an area is inundated. So this is somewhat obvious, like it's higher towards the seaward and it decreases as you move landward. But there's also a feedback loop that may occur here. So an increased hydro period may result in greater sedimentation, as an increased inundation time allows some more sediment settling to occur. And sea level rise will have an impact, an increase on the hydro period. So there's our increased sedimentation with a higher hydro period. So another way that mangroves can adapt to sea level rise is by landward lateral migration. It's not just as simple as moving a boundary. Coastal wetlands may be restricted by the coastal squeeze and have nowhere to move. And this is it's not always ideal for them just to move. So they may be encroaching upon another important ecosystem. So down here in Southeast Australia, we see mangrove encroaching into salt marsh communities, which is an endangered ecological community. What we do know, though, is that inundation beyond physiological tolerances will lead to coastal wetland loss, and those ecosystem services they provide will disappear alongside them. So understanding surface elevation is critical in determining their vulnerability to sea level rise. But surface elevation processes are really complex. They're a combination of both surface and subsurface processes. These include biological surface processes. Someone got their hand raised. Sorry. So they include both biological surface processes, such as crabs burrowing on the surface, and So these are our biological processes, like the crabs, and then we've also got surface physical processes such as sedimentation and erosion. And then we've also got below ground biological processes such as root growth that will increase the sediment volume. And these are also paired with some physical processes such as autocompaction, which will move the whole system down. And it's a culmination of all these processes that will result in an overall surface elevation change. These processes are then influenced by several indirect drivers, such as sediment availability or storms that may exert pressure across various spatial and temporal scales. But importantly, it's sediment accretion and root growth that will increase the overall surface elevation of our coastal wetlands. So to understand surface elevation, we use a method developed by Don Cahoon and colleagues of the US Geological Survey. It's had a few iterations of the design, but it's been in development since the 1980s. And so it's been designed to answer these questions around surface elevation and vulnerability. So the RSET measures very precisely the overall elevation change in our coastal wetland. Stainless steel rods are driven many, many meters, like 10 to 20 meters, to a point of refusal in the mangrove sediment and fixed into place. So this forms a permanent benchmark from which we can come along and measure the elevation relative to this benchmark by attaching the RSET to the constant plane. The frequency of these measurements really depends on your research question, but generally these are, annual measurements being made. So very long-term, slow processes that over a long period of data capture will get some answers from. These are usually paired with 3 marker horizons, and this gives us the vertical accretion. So marker horizons are often a pale substance like feldspar laid down at the baseline measurement, and that can delineate the surface processes that have occurred since its installation. From that, we can determine the overall subsurface change. Okay. So to ensure that these benchmarks are not just isolated, we get the vertical elevation relative to a consistent reference. So in Australia, we would use Australian height datum, and we do this using a global navigation system. So GNSS, or an RTK GPS, and we can get an accurate elevation of that benchmark. This can then be referenced independently to the nearest tidal gauge, providing sea level data as well as some deep geological processes. So this is us installing an RSET in East Timor. So the benchmark is being installed. These stainless steel rods are being driven in with a hammer drill, and you can see that we're doing this off a platform so as to not disturb the sediment. All right, so this method has been employed in wetlands globally, and it's considered to be the global standard for monitoring coastal wetland vulnerability to sea level rise. An example of the application of the global RSET data was published just last year, and Santiland and colleagues used multiple lines of evidence, including over 600 RSETs, to draw conclusions about the persistence of coastal wetlands under various sea level rise scenarios. And it showed that if rates of regional sea level rise were to exceed 7 millimeters per year, there's a high probability of losing these coastal wetlands. This is us measuring an RSET. So we've got the permanent benchmark in place, and we've attached some equipment to form a permanent plane of reference, and we've lowered these fiberglass pins very gently onto the sediment surface. All right, so there's also an emerging network of sets around Australia, both in mangroves and in salt marsh, and researchers are using this to answer questions around what rate of carbon is being captured and stored in the sediment, are restoration efforts working, and how are these systems changing through time. And from an Australia perspective, we can start to use this empirical data to hopefully inform coastal wetland management decisions, interventions, and hopefully guide some good policy. All right, so let's come down a bit further and look at one location in Australia where RSETs have been deployed. In 2016, we installed 42 RSETs across 5 sites in Darwin Harbour. You can see in the top right-hand corner, this is what an RSET looks like for most of the year. This is when it's not being measured. It's just a little stick in the mud. So if you see one of these when you're out and about, please just leave it alone. We want to measure the processes that are occurring, not your footprints. So Darwin Harbour in the Northern Territory, it's home to over 20,000 hectares of mangroves of very diverse species, and it's considered to be in near pristine condition. So Darwin Harbour has a macrotidal range of over 8 metres, and this has led to the development of a wide mangrove forest forming parallel bands of floristic assemblages. So this pattern is driven in part by the hydro period. So RSETs as well as sediment cores have been taken across the tidal profile, and I've grouped these into 4 broad functional groups. This represents some detailed spatial resolution to the geomorphic and ecological processes at work in the Darwin Harbour mangroves. All right, so we've got some results from this very slow science approach. So with years of data, we can begin to answer some spatial and temporal questions regarding the contemporary surface elevation dynamics. So we found that increases in elevation in Darwin Harbour occur largely through the addition of sediment, with below ground contributions really being limited. So the graphs show the marker horizons as open symbol, and this is our sedimentation rate, and they're higher than the rates of the overall surface elevation change, which is indicated by the black symbols, and that's from our sets. We're also seeing that riverine sites are receiving more sediment, thus more surface elevation than our harbour sites. So when we apply this theoretical curve, it's supported in the data at the riverine sites where sedimentation is high in the seaweed, with little sediment reaching the inner and landward forest. However, our harbour sites have low sedimentation occurring across the tidal profile, and indeed a bit of a net loss at the seaward side. So this indicates that vulnerability is based on broader geomorphic location and not necessarily just elevation alone. I had a really interesting finding. I've had lightning strike 2 of my assets. So lightning in a mangrove system will kill all the trees in a circle, and we had about a 25-metre canopy gap occur where all the trees had died. Right in the middle was my asset. This interestingly has shown the rapid loss of elevation due to fine root death. And while a paired asset, so this one here, it's in the same community, it's about 50 metres away, it was not directly affected by lightning in that all the trees were still alive, and it's had some gain in elevation. But so far, no recruitment of mangrove seedlings has been supported at this site, as it's already below mean sea level. So showing that there's an obvious threshold or tipping point that's been crossed at this location. All right, that's it. That's my 13 minutes. Thanks, everyone. I'd love to take your questions at the end, but I'll hand over to Tim now.
Thanks, Maddie. That was awesome. Just give me 1 second. Beryl showed me a new way to do this, so I hope I get it right. Okay. So, look, thank you very much for having me. My name is Tim Rawling. As Beryl said, I'm the director of AusScope, which is another one of the NCRIS capabilities for the Earth and Geospatial Sciences. And I'm going to talk a little bit about some of the new investments we're making in coastal monitoring. But to do that, I need to first talk about Coastar, which is a program that many of you may be aware of, or a collaboration. And I feel a little bit embarrassed because as I pulled the slides together, I realized that whilst my name's on the top, the majority of the slides are other people's, and the majority of the work I'm talking about are other people's. So I just want to recognize Dan Iridiakonu, who's done an enormous amount of work on this Coastar project, as well as Michelle Hoople from IMOS. And some of the other slides are from Steve and Micklethwaite and Mitch Harley. But particularly Dan and Michelle, who have really been driving this program, and much of the work I'm talking about is really theirs. So I'd also like to start by acknowledging the traditional owners of the land on which AusScope infrastructure operates, and recognise and pay respect to their elders past and present. And we recognise the connection they've had with land, sea and sky and waterways for tens of thousands of years. For me today, I'm on Wurundjeri country of the Kulin Nation. Okay, so I'll start by giving some background, and this probably isn't going to be news to any of you, but it gives you a bit of a sense of why we're interested in doing what we're doing. Just a sec, I've got something sitting in front of my screen. There we go, that's better. So as you're all aware, look, the current state of the coast is changing, and it's changing rapidly and in unprecedented ways. And, you know, many of you probably were involved in putting together state of environment reports, but the 2022 State of the Environment report shows that our environment's deteriorating, climate change is threatening all of our native ecosystems. Environmental management isn't particularly well coordinated across the country, and environmental decline is affecting all human well-being. And that's particularly true of coastal regions. You know, many of our population centres lie along the coast, industry lies along the coast. An enormous component of the Australian population live and use the coast, not only for you know, productivity, but also for their own well-being. So it's an incredibly important part of our society. We also have huge economies that rely on the coast, and you know, some of those we've sort of mentioned today. You know, the blue economy is growing enormously, but there are other aspects of our economy that are totally dependent on a healthy coastline. And there are some really complicated, intricate relationships between some of the older, you know, probably less sustainable industries that we still operate in this country, like oil and gas, and groundwater systems, and CO2 storage and geothermal systems, and they all operate in these coastal regions and they impact coastal environments. So we need to understand how the coast reacts to all of these different types of industries and anthropogenic use of these systems. So basically we need a lot more data. So the challenge, as I've said, you know, most of us live near the coast, and what we really recognised was that there was a real gap in some of the data to support decision-making around these coastal regions. And in many ways, that was partly because the coasts are such complicated places to operate. And, you know, some groups that collect data like IMOS and AuScope, who collect data within their discipline areas, found the coast was like that sort of boundary between our two areas of influence, and I guess was not ignored, but was sort of very challenging to identify how we could do that effectively. And so part of what we're trying to address with this program is to bring a much more coordinated response to collecting data in these regions. The other part of the problem is that there are so many organisations and groups, from you know, federal authorities to state authorities to local council authorities to local land management groups and local catchment management authorities, that all have a stake in how we monitor and manage the coast, and all of them have an interest in how we collect data. So that also creates opportunities, but it also creates many challenges for us. So in order to address this, a number of the NCRIS capabilities, and I'm sure given you're in a TERN seminar, you all know what NCRIS is, but it's the National Collaborative Research Infrastructure Strategy, and it funds investment in research infrastructure across numerous different discipline areas across Australia. And there are a group of us that get together in a group called NESIF. We've got lots of acronyms, we love them. NESIF is not a great one, but it stands for the National Earth and Environmental Science Facilities Forum. And in a number of those meetings, we identified this gap, I guess, and we started to think about ways that we could address that. And in doing so, we brought together all of those NCRIS capabilities that are listed down the left-hand side of this slide. And again, I nod to Michelle here, because Michelle was really the driving force behind much of this, but other people like Andy Hogg, like Beryl, have been absolutely instrumental in this process as well. So what we did was we brought together sort of a coalition of aligned NCRIS organisations, and we identified what the problem was in our mind, but we recognised that it was much bigger than we could identify. So we initially created this concept called Coastar. We had a vision to develop a research infrastructure that connected land and sea. And we wanted to gather comprehensive and integrated scientific data from diverse sources, enabling us to better understand, predict, and address opportunities and risks facing Australia's coast for all people. In bringing that group together and under the sometimes complex funding arrangements in which we operate through the NCRIS program, we had the opportunity to put in some proposals initially for some funding. So some of that was for actual infrastructure. So I'll talk a bit about some of that in a minute. But some of it was also to develop a pilot around what this Coastar program would look like, and to really fund an engagement process over the course of 12 months, where we would go out and find out what the gaps were and what the community needed. And that would then underpin a second submission to the Commonwealth to try to get some additional funding to fill those gaps and build new infrastructure to monitor various aspects of the coast. So the areas that we really identified were we needed to collect new novel data sets and data streams. We needed to aggregate existing data sets that are already out there but are difficult to access. We needed to support modelling and forecasting, so the sort of work that Access NRI does, and to understand the impacts and to be able to predict the impacts of climate change, sea level rise, and other things on the environment and on the coast. We needed to enhance and add value to existing programs, and we needed to be able to provide all of this data in ways that was going to inform decision making. So it was going to be usable by the community that needed it, not just to support the science cohort, I guess. So as I said, we were successful in those bids, and part of what we did was, what we got was some funding to support this consultation process that, as I've said multiple times now, Michelle and Dan have really been driving. And that's been taking place since about November of last year. And Dan and Michelle and others have engaged with an enormous number of people in the community from all parts of the community. And many of you, I'm sure, would have been involved in that process. They've identified an enormous amount of opportunity for new investments, and I'm not going to go into any of those because that's not my area. But we've also identified that we need to prioritise a few things. So that would be national scale and broad multi-end user data use cases, I guess. And also we need to maximise the capability of the existing NCRIS programs and our partners by increasing the level of collaboration that we have. So this diagram really nicely shows, I guess, kind of where we all sat, and there are other things in there that aren't NCRIS data sets. There's data sets in there that are other government data sets and things. But this shows, you know, a coastal environment, and it shows that there's a whole bunch of data that we're all collecting independently, and that Coastar is a way of tying all of that together. And this is quite a neat little diagram, but one Michelle put together recently shows the real complexity of how that actually looks. So we identified a number of themes that have come out of the consultations, and you can see things like biodiversity, community wellbeing, habitat cover, human settlements, coastal water quality, erosion, estuarine water quality, and inundation were really the big ticket items. And we've also been able to map areas of existing capability or opportunity for growing capability across to the existing NCRIS capabilities. And you can see that that is it's a bit of a spaghetti diagram, but it shows the immense capability that already exists and the way that we're going to have to collaborate to actually make any meaningful impression on collecting these integrated data sets for coastal monitoring. We also put in some proposals for what we called no regrets funding. Now, the no regrets funding was funding that we knew we needed before we went out for consultation, that had been on the agenda for some time and that was already driven by a strong community need. Ozscope, IMOS and TERN all put in various proposals as part of that. And Ozscope was successful in getting some funding to support some new drone monitoring capability, some fixed cameras, some GIA modelling, which is glacial isostatic adjustment modelling. I won't talk about that, but I'll talk about the others in a minute. IMOS put in a number of proposals around coastal wave observing and coastal moorings. And TERN, we've already heard about the surface elevation tables from Maddie. So I thought what I'd do is just give you a little brief update on what Ozscope is for those of you that are not familiar with us. So as Beryl indicated, Ozscope is the NCRIS capability that supports Earth and geospatial sciences. And we operate in a very similar way to the way that TERN does. So we have a number of hard infrastructures, I guess, infrastructure systems that we deploy in the field, observational infrastructures. So things like seismometers, magnetotellurics, which is a geophysical method. We support the national deployment of these and we support the data collection from these instruments. We have a number of things that are related to understanding or characterising the Earth and drill core. We have education and outreach programs. We also have a strong positioning and geodesy program, which includes positioning telescopes, VLBI telescopes, but also includes a GNSS network across Australia. Then we have a whole suite of data delivery and discovery systems and data repositories, which we won't go into at all, and also some simulation and analysis tools and platforms that sit on top of that to allow us to add value to that data. We've collaborated in the past with TERN, and we collaborate on our CZO project, which is the Critical Zone Observatory, in doing stuff like heat flow and some borehole monitoring with TERN in those environments. And like TERN, we work with an enormous number of partners across Australia to deliver these systems. So look, just to finish, I'll give you just a brief update on what we're doing now with this No Regrets funding and what we're going to do in the future. So with the Coastar No Regrets funding, there were sort of three aspects that we invested in. Two I'm going to talk about here. The first is the drone monitoring capability. So this includes a couple of aspects. One is the VTOL drones. So we've acquired some VTOL drones, which are these vertical takeoff and landing drones. They're allowed you to fly long distances and carry larger payloads. And as part of that, we're providing access to the community to use the drones, to use some very sophisticated sensors like bathymetric radar, LiDAR, which allow you to do some really nice things like this imaging of the coral system in the bottom left. And we're also providing access to pilots so that you don't have to get CASA training if you just want to do some very short-term monitoring using these systems. We also have supported a large citizen science project that Dan has been involved in running for a number of years, which the VCMP data up in the top right there is developed from. And so these are these ongoing regular monitoring surveys of coastal regions, currently in Victoria, but we're going to expand that to a national program where citizens learn how to fly DJI drones, collect data regularly and upload that into a data repository that provides data about volumetric change in these coastal environments. And finally, we've also supported some fixed camera and fixed LiDAR stations, which give information about change within a single beach environment. So the image on the top left is Mitch Harley at Narrabeen installing some of these instruments where you can take on long-term video footage. You can show change in enormous detail. You can also look at beach use and things. So you can use AIs to work out how many people are on the beach at different times, what sort of impacts that has on activity and anthropogenic impact. We also have one other project which is sort of funded through Auscope directly, but it's trying to look at some additional uses of drones, in particular with a hyperspectral camera. So this might be of interest to many in your community. Here it's being used for a geological assessment of Mary Kathleen mine, which is a uranium mine. Or was a uranium mine, but obviously there's some applications of these sorts of sensors in the ecosystem community as well. And we're looking at some of these drones that can actually land and sit on the surface and take measurements for long periods of time and then hop to another site and collect other data. So some sort of novel drone use. So I'll finish by saying what's next. So basically, from the point of view of Coastar, the process is underway and continues. There are opportunities still to be involved. So we hope that you will, if you have an interest in this space, be involved in the consultation as it continues and make sure that any gaps you can identify or your community knows of will be captured in that data gathering exercise. From Auscope, we can't preempt what's going to come out of this process, but we do know that there's an enormous need for more GNSS integration in coastal regions, particularly with respect to some of the stuff that Maddie talked about, like tying the tide data to the surface elevation and surface ground motion data. We want to do more INSAR integration. We want to focus on fair and care data of some management and protocols around the coastal monitoring data. And we also want to understand ways that we can provide analytics. So if anybody has not looked at the European Ground Motion Service portal. You can lose days in there. This is just an image, obviously, of Northern Europe, and you can see the isostatic response to the melting of the ice sheets after the last glacial. But you can zoom into these maps and see enormous detail about surface and ground motion from a variety of causes. So thank you for having me. I hope I haven't gone too long, but real massive thank you to Michelle and Dan, as I've already said, and to Beryl for including us in this presentation.
Thank you very much, Tim and Maddie and Ruth. They've been fantastic presentations. Perhaps you can all turn your cameras on. And I think we had a really good summary there from Tim that it's a happening area. And I think we do have a question. So somebody who's interested in data platforms used by NCRIS and citizen science data collection. And will the high quality scientific rigorous data for biodiversity be transferred to state platforms to ensure state government conservation use? I might actually say that there is a cross-jurisdictional group working at the moment to bring all the data to one place so that we get a collective view, because as we've been emphasising in this talk, it's really complex and it can't be tackled locally. It can't be tackled in short time periods. Ruth emphasised the long-term need. You can't just pick a season or a point in time. Maddie's emphasised the fact that yes, things can adapt, but maybe there are limits to adaptation. So obviously we all need a big picture view of this. And in our consultations, we encourage people from anywhere internationally to join that, because oceans and coasts are shared by everyone at some point. I think that's the only, then we have another question. All speakers, will there be any other outcomes for communities of traditional custodians of the land on which your work has been conducted? What kind of things are you looking for? Does somebody want to quickly tackle that? Very quickly.
I can speak to that, and I can speak to, if you may, the challenge. I've been working in Western Australia for many years, I think since 2009. There have been changes, very positive changes in land ownership and involvement of Indigenous communities. I think in the way our so I'm entirely ARC funded, for example. The way our funding systems work make it very difficult to employ long-term Indigenous support to field sites, for example, and inclusion, properly remunerated inclusion of say Indigenous rangers and training of Indigenous rangers into these programs. And I think it's programs like what Beryl and Tim are running, which are these long-term things, really have, I think, a responsibility to create those opportunities to enable those long-term commitments. We're working on land of Indigenous people. The involvement has to be there, but it also has to be something long-term so that interaction can occur. And these things are very hard to achieve on 3-year grant cycles.
Good. Everyone happy with that? Maddie, Tim? Okay, I might close our webinar today with a huge thank you to our speakers again, and also to the audience, because we've had some good chat going on and questions, and I see we're going to have some follow-up from other countries in everything. So now is the time for everyone to be thinking about what they want to support their research in coasts, and contact any of us. Put that forward and we will take it into account in our future funding bids. We don't always know how successful they're going to be, but just to remind everyone that we continue these webinars every second month, and the next one is going to be about the fantastic role that Australia serves for international science space missions that are looking at things like biomass and so on, and the role that Australia plays in validating all of that data. So do join us for the next one. And oops, I can't get my thing to go, but thank you everyone, and please send any feedback or questions through to us. We look forward to seeing you next time. Bye-bye.